We're taking pictures of these objects with astonishing precision. It's like, whoa.
When the James Webb Space Telescope launched on Christmas Day 2021, we knew its groundbreaking capabilities had the potential to revolutionize our understanding of the universe. And this incredible spacecraft has not disappointed. Right from its first observations, James Webb has given astronomers new puzzles to solve and new questions to pursue. From theories of early galaxies to the expansion of the universe, our premier observatory has fundamentally challenged what we thought we knew. That has raised some concerns that the history of the early universe needs to be rewritten. In this dilemma, Bill Nye, CEO of the Planetary Society, has broken the silence on the most stunning discoveries captured by James Webb, delivering us an awesome explanation of how James Webb just upends all we think we know about the universe.
Which would change everything. It would change the way you and I feel about being alive.
Join us as we dig deep into how James Webb just shatters our cosmos. Number 1. Big, bright galaxies at cosmic dawn. Before James Webb, astronomers thought galaxies began as small clouds of gas, dust, and stars that gradually grew into the island universes we see today. But the telescope's ability to see infrared radiation allows it to peer farther into space and thus further back in time to when galaxies first formed.
If you could somehow be there with your spacesuit looking out, you wouldn't see any of these things. The image was taken in infrared wavelengths.
But when James Webb turns its razor-sharp eyes into the past, it has found several of the enormous distant galaxies that should not exist. Nobody expected them. They were not supposed to be there. And now, nobody can explain how they had formed. Galaxies nearly as massive as the Milky Way and full of mature red stars seem to be dispersed in deep field images obtained by James Webb during its early observation campaign, and they are giving astronomers a headache. These galaxies, described in a new study based on Webb's first data release, are so far away that they appear only as tiny reddish dots to the powerful telescope. By analyzing the light emitted by these galaxies, astronomers established that they were viewing them in our universe's infancy within only 500 million years of the Big Bang. Its latest discovery is a galaxy designated JADES GS Z1410. Dating to only 300 million years after the Big Bang, it is the most ancient galaxy yet observed. Astronomers calculate the distance of objects like JADES GS Z1410 by examining their so-called redshift value. Because the universe is expanding, the wavelength of light waves is stretched as they move through space. This phenomenon is known as redshift because it moves light toward the infrared region of the electromagnetic spectrum. The further away a given source of light is, the longer it has to travel to get to us, and the more it is redshifted along the way. James Webb's instrumentation, as Bill Nye emphasized, is designed to examine the dramatically redshifted light from distant galaxies, and its sensitivity to this light has allowed it to set record after record for the most distant object ever observed.
This instrument can detect all these objects in the infrared, and then we, here on Earth, take those data and shift it so that it's visible.
For instance, JADES GS Z1410's redshift value of 14.32 makes it the new holder of this record. However, even for Webb's objects as far away as JADES GS Z1410 present a challenge. The extreme faintness of their light often makes it difficult to derive enough information about them to draw any definitive conclusions about their properties. JADES Z1410 first caught astronomers' attention because it appeared to defy this trend. Despite its extreme redshift, the galaxy was unusually bright. This brightness was initially assumed to be due to its proximity in the sky to another, closer galaxy. However, it soon became clear that JADES GS Z1410 was something special, and that its remarkable luminosity was all its own. This made it a prime candidate for closer examination, and in October last year, Webb's near-infrared camera was trained at it for 5 full days. The data provided by this close observation allowed scientists to conduct a detailed examination of the galaxy's spectral signature, which in turn allowed for close investigation of the galaxy's composition and evolution, the results of which are published in a separate paper. This paper suggests that JD's GS 1410 contained 500 million solar masses in stars, with a strong burst of star formation in the most recent few million years. This is far earlier than pre-James Webb models deemed possible. It is stunning that the universe can make such a galaxy in only 300 million years. But the Webb telescope has provided a steady stream of such stunning revelations, and in doing so, revolutionized our understanding of how and when the first galaxies coalesced from the primordial gas released in the Big Bang. To be precise, we have extended our reach into the cosmic past by 40% during the first 18 months of Webb's operations. The existence of luminous galaxies like JD's GS 1410 in the early universe has proven a further surprise to scientists. This galaxy and similar objects are promising subjects for further observation, as their remarkable brightness dangles the tantalizing prospect of allowing us to peer right back to what calls the cosmic dawn, the period where the first galaxies were born. Another remarkable observation, James Webb also have found more advanced structures in some spiral galaxies around cosmic noon, when the universe was 2 billion to 3 billion years old, and making stars at their greatest rate. Number 2. Early supermassive black holes. Everyone knows that black holes grow as they devour passing stars and clouds of gas and dust. So, it comes as a surprise to find supermassive black holes lurking in the early universe when they haven't had much time to chow on their surroundings. James Webb has discovered several black holes weighing about 1 billion solar masses, dating to 800 million years after the Big Bang. An equally important discovery, astronomers using the James Webb Space Telescope have detected the earliest known black hole. Located more than 13 billion light-years away, it dates to a mere 400 million years after the Big Bang. The black hole lies at the center of a galaxy called GN-Z11, which, at the time of its discovery in 2016, was the oldest galaxy ever spotted. But such supermassive black holes are surrounded by mystery, especially when seen earlier than 1 billion years in the 13.8 billion year history of the universe. That is because the continuous merger process of black holes, by which scientists think supermassive black holes grow over time, should take many billions of years to proceed. So, how could these giant voids exist only about 1 billion years after the Big Bang? Well, one suggestion is that they got a head start, forming from so-called heavy seed black holes. And by using James Webb to observe faint light coming from stars in the host galaxies of 6 ancient quasars, for the first time, scientists collected evidence that supermassive black holes in the early universe indeed grew from heavy seeds. Perhaps even more importantly, the telescope has turned up much smaller, supermassive black holes with masses from 1 million to tens of millions of suns at even earlier times. This could provide astronomers with enough data to figure out how these behemoths evolve. Number 3. Dust in the universe's youth. Dust appears all around us, in fluffy bunnies lurking under our beds, in dark clouds blocking our view of the Milky Way, and as signatures in the spectra of distant galaxies. Most dust contains carbon, so it's a relative latecomer to the cosmos because early stars had to forge the element from their initial supplies of hydrogen and helium. But in a stunning observation, James Webb has detected the earliest known carbon dust, one of signs of the element that forms the backbone of all life in 10 different galaxies that existed as early as 1 billion years after the Big Bang. The detection of carbon dust so soon after the Big Bang could shake up theories surrounding the chemical evolution of the universe. According to current theory, the early universe was made up of mostly hydrogen and helium with tiny traces of some heavier elements, meaning the first stars and galaxies should have the same composition of just these light elements. Conventional models of the universe's chemical evolution suggest that heavy elements like carbon and oxygen are forged in the nuclear furnaces at the heart of stars. When the first stars ran out of the fuel for nuclear fusion and reached the end of their lives, they exploded in supernovas, dispersing the material they had forged through the cosmos. This stellar matter is integrated into interstellar dust. When dense patches of this dust collapse, this material becomes the building blocks of the next generation of stars, which are thus richer in heavy elements and sit in similarly enriched galaxies. But this is challenged by the findings made by James Webb, as some of the galaxies it saw carbon dust in are estimated to be somewhere in the region of 10 million years old. That implies there must be a creation and dispersal method for carbon that works on a relatively short timescale. The findings exemplify the kind of science that wouldn't have been possible before the James Webb Space Telescope, which began observing the universe and delivering data and images in July 2022. Number 4. Tightening cosmic tension. Astronomers have known for decades that the universe is expanding. When they use telescopes to observe faraway galaxies, they see that these galaxies are moving away from Earth. But as astronomers have studied these distances, they've learned that the universe is not just expanding, its rate of expansion is accelerating. And that expansion rate is even faster than the leading theory predicts it should be, leaving cosmologists puzzled and looking for new explanations. Scientists call the source of this acceleration dark energy. We're not quite sure what drives dark energy or how it works, but we think its behavior could be explained by a cosmological constant, which is a property of space-time that contributes to the expansion of the universe. Albert Einstein originally came up with this constant. He marked it with a lambda in his theory of general relativity. With a cosmological constant, as the universe expands, the energy density of the cosmological constant stays the same. Imagine a box full of particles. If the volume of the box increases, the density of particles would decrease as they spread out to take up all the space in the box. Now imagine the same box, but as the volume increases, the density of the particles stays the same. It doesn't seem intuitive, right? That the energy density of the cosmological constant does not decrease as the universe expands is, of course, very weird. But this property helps explain the accelerating universe. Right now, the leading theory, or standard model, of cosmology is called lambda CDM. Lambda denotes the cosmological constant describing dark energy, and CDM stands for cold, dark matter. This model describes both the acceleration of the universe in its late stages as well as the expansion rate in its early days. Specifically, the lambda CDM explains observations of the cosmic microwave background, which is the afterglow of microwave radiation from when the universe was in a hot, dense state about 300,000 years after the Big Bang. Observations using the Planck satellite, which measures the cosmic microwave background, led scientists to create the lambda CDM model. Fitting the lambda CDM model to the cosmic microwave background allows physicists to predict the value of the Hubble constant, which isn't actually a constant, but a measurement describing the universe's current expansion rate. But the lambda CDM model isn't perfect. The expansion rate scientists have calculated by measuring distances to galaxies, and the expansion rate as described in lambda CDM using observations of the cosmic microwave background don't line up. Astrophysicists call that disagreement the Hubble tension. James Webb has now confirmed this higher value to much better precision. The discrepancy between the two methods suggests that scientists are missing something in how the universe works, or have made multiple errors in their measurements that all act in the same direction. Number 5. Studying star formation in detail. Stars form in dense clouds of gas and dust. Unfortunately, dust blocks visible light, shielding much of the process from view. But now, thanks to its infrared eyes, James Webb penetrates dust, opening a new window into star birth. For example, it has revealed thousands of new stars buried deep within the Eagle Nebula, M16, that Hubble couldn't reach. In addition, the Supreme Space Observatory also showed remarkable detail in a section of the nearby Rho Ophiuchi complex. The telescope's images have revealed dozens of young low-mass stars as well as the jets they emit, which light up surrounding clouds of molecular hydrogen. And in its latest observation, James Webb has unlocked another achievement. This time, the dynamic telescope has peered into the heart of a nearby star-forming region and imaged something astronomers have longed to see: aligned bipolar jets. James Webb's observing time is in high demand, and when one group of researchers got their turn, they pointed the infrared telescope at the Serpens Nebula. It's a young nearby star-forming region known for being the home of the famous Pillars of Creation. The Hubble Space Telescope made the pillars famous, and the telescope followed that up with its own stunning image. But this time, researchers weren't focusing on the pillars. As a nearby star-forming region, Serpens Nebula is a natural laboratory to study how stars form and to try to answer some outstanding questions about the process. The Webb delivered. A team of astronomers from the USA, India, and Taiwan examined the region and published their results in a paper titled, "Why Are Almost All the Protostellar Outflows Aligned in Serpens Main?" The lead author is Joel Green from the Space Science Telescope Institute. Stars form when giant molecular clouds of hydrogen collapse. They start out as protostars, objects that haven't begun fusion yet and are still acquiring mass. As they grow, gas from the cloud gathers in a swirling accretion ring around the star. As it moves, the gas heats up and emits light. As the cloud collapses into a protostar, some of the energy is converted into angular momentum and the young star spins. For the young star to keep acquiring mass, some of the spin needs to be removed. That happens as the swirling accretion disk emits some of the gas from bipolar jets, also called protostellar outflows. They're part of how stars regulate themselves as they grow, and they come from the young star's poles, perpendicular to the spin. The magnetic fields around the star drive the jets out of the poles. But there's a lot more detail in the process and some outstanding questions. Stars don't form in isolation. They usually form in clusters or groups, and there are intermingling magnetic fields at work. At only 1,300 light-years away, Serpens Nebula is a good place to try to spy some of this detail. Until James Webb came along, the detail was hidden from even our most powerful telescopes, and astrophysicists were left to theorize with what they could observe. Number 6. A dusty supernova remnant. A supernova is what happens when a star has reached the end of its life and explodes in a brilliant burst of light. Supernovas can briefly outshine entire galaxies and radiate more energy than our sun will in its entire lifetime. They're also the primary source of heavy elements in the universe. According to NASA, supernovas are the largest explosion that takes place in space. And now, in a groundbreaking astronomical discovery, the James Webb Space Telescope has captured detailed images of a supernova explosion, providing unprecedented insights into the life cycle of stars. This event marks a significant milestone in our understanding of cosmic phenomena. Just 340 years ago, light from an exploding star first reached Earth. Today, we see this supernova's remnant, known as Cassiopeia A, Cas-A, as a 10-light-year-wide debris shell. Cas-A's stunning beauty in the infrared comes from wispy tendrils of gas and the soft glow of warm dust. The dust intrigues astronomers because it is a basic building block of planets and life. They suspect most cosmic dust forms from the heavy elements supernovae eject, though previous studies couldn't explain the amount of this material seen in early galaxies. Scientists hope James Webb's observations of Cas-A and other supernova remnants can shed more light on its creation. Number 7. A jumbo surprise. At the end of 2023, astronomers made a startling discovery in the Orion Nebula. Using James Webb, the team found 40 pairs of planetary mass objects, none of which orbit a star. They're called Jupiter mass binary objects, or JUMBOs. In short, this discovery directly challenged both star birth and planet formation theories. The origins of these orbs remained unknown, and it was unclear how such a large collection of pairs of these bodies came to wander the Orion stellar nursery, which is located around 1,350 light-years from Earth. JUMBOs themselves have been a challenge to explain because their existence doesn't quite conform to classically accepted models of star formation or planet formation. As hot, gassy, and binary bodies, JUMBOs may initially seem as if they form when overly dense regions in a clouds of gas and dust collapse. That's how stars form, and is even the mechanism followed by so-called failed stars, or brown dwarfs, which get their nickname from the fact they fail to gather enough mass to fuse hydrogen to helium in their cores, a defining stellar characteristic. However, JUMBOs likely take a different route into reality. The chance of a star possessing a binary partner, for instance, diminishes significantly as the masses of those stars decreases. For example, around 75% of massive stars exist in binary pairings, but only 50% of stars with masses similar to the Sun are found with a stellar partner. And the chance of finding a brown dwarf with masses around 0.75 times that of the Sun in a binary is vanishingly small, approaching 0%. Brown dwarfs, on average, have masses around 75 times that of Jupiter. Thus, stars less massive than this, one can reason, should never exist in binaries. Certainly not frequently enough to find 40 in the same nebula. JUMBOs have masses under the lower end of brown dwarfs, less than 13 times the mass of Jupiter. So, what's going on? Furthermore, JUMBOs can't be explained with standard planetary formation models either. These are models that would see them born from leftover gas around a parent star, or stars if you're working with a binary system. That is because, though we know planets are regularly kicked from their home systems to become rogue planets, aka cosmic orphans wandering the cosmos without a parent star, this process should be so violent that it splits apart any possible gravitationally bound planets. The fact astronomers found 40 pairs of JUMBOs in the Orion Nebula alone therefore seems to rule out some freak ejection event that led to a planetary pair being ejected together without being split up. So, having said that, understanding the formation of JUMBOs helps us challenge and refine the prevailing theories of planet formation. Forthcoming observations from James Webb may help us do just that, offering new insights with each observation that will help us better formulate new theories of giant planet formation. Number 8. A molecular exoplanet revolution. Although images draw the most attention, spectroscopy plays a huge role in James Webb's explorations. It allows astronomers to determine the redshift and thus distance of faraway galaxies, and to analyze the chemical composition of astronomical objects. Nowhere is this more important than in the study of exoplanet atmospheres, where Webb's infrared capabilities allow it to detect molecules invisible in optical light.
And this telescope is so sensitive that you can infer the composition of the atmosphere.
Among its many discoveries, the Premier telescope has detected potential biosignature elements in the atmosphere of the exoplanet K2-18b, a super-Earth located around 120 light-years from Earth. Though many exoplanets are extreme, violent, or at least alien in nature, whether they're blasted by intense radiation from their stars, lack a solid surface, or are frozen relics at the edge of their systems, K2-18b was a tantalizing target in the search for life because it is rather similar to our planet. K2-18b is between 2 and 3 times the width of Earth with 8.6 times the mass of our planet. It's also located in the habitable zone of its star, the region neither too hot nor too cold to support liquid water. The exoplanet is thus theorized to be an ocean, or Hycean world, replete with liquid water, a vital ingredient for life as we know it. However, unlike Earth, the atmosphere of this exoplanet seems to be mainly hydrogen rather than nitrogen. The key takeaway from the investigation of K2-18b, conducted by University of Cambridge scientists using the James Webb Space Telescope, was the discovery of carbon dioxide and methane. These molecules were detected without traces of ammonia, which indicated that this should indeed be a Hycean world with a vast ocean under a hydrogen-rich atmosphere. But there was also the hint of something else, something very exciting. A bold idea. There must be something on K2-18b, possibly a life form, producing it at 20 times the rate found on Earth. Interestingly, in a recent finding, the James Webb Space Telescope has discovered stormy weather in the sky of two brown dwarfs, in the most detailed weather report yet from such failed stars. The two brown dwarfs form a binary pair called WISE 1049ab that was discovered by NASA's Wide Field Infrared Survey Explorer, or WISE, in 2013. The duo sits just 6.5 light-years away from us. They are the closest brown dwarfs to our Sun, and thus make an excellent target for the James Webb Space Telescope's powerful infrared instruments. A brown dwarf is an object that isn't quite massive enough to ignite the nuclear fusion of hydrogen to helium in its core and become a fully fledged star, yet is also considered too massive to be a planet and thought to form like stars do via the gravitational collapse of a cloud of molecular gas. As such, brown dwarfs are thought of as a missing link between gas giant planets like Jupiter and the lowest mass stars, M dwarfs. Previous observations have probed the atmosphere of various brown dwarfs, but they have always been limited to time-averaged snapshots, meaning we could not see things in the brown dwarf atmosphere changing with time. However, brown dwarfs are fast rotators. WISE 1049a spins on its axis once every 7 hours and B once every 5 hours. And the conditions in their atmospheres can alter over time, meaning that previous observations that didn't factor in the object's evolutions could have missed lots of variability. However, the Webb telescope does have the ability to detect these changes over time. A team led by Beth Biller of the University of Edinburgh observed WISE 1049ab for 8 hours with James Webb's MIRI, and then immediately afterward for another 7 hours with its NIR spec. The researchers found that both brown dwarfs are covered in tumultuous clouds, probably composed of silicate grains, sweltering in temperatures between 875 degrees Celsius and 1026 degrees Celsius. In other words, hot sand is being blown in the winds of the brown dwarfs. The absorption signatures of carbon monoxide, methane, and water vapor were also identified. Intriguingly, the light curve for each brown dwarf, a graph of each brown dwarf's brightness over time, displays considerable variability. This has been interpreted as stormy conditions, blowing clouds at various altitudes, and gaps appearing between those clouds that allows for views into deeper layers of the atmosphere. The light curves also show peaks at specific wavelengths, carbon monoxide at 2.3 microns and 4.2 microns, millionths of a meter, methane at 3.3 microns, and silicate grains tentatively at 8.3 microns to 8.5 microns. Biller's team interpret the peaks at these wavelengths as indicating 3 different layers, where there is a significant change in atmospheric pressure on each brown dwarf. There's a deep layer producing signals greater than 2.3 microns but less than 8.5 microns, an intermediate altitude layer absorbing light at between 2.3 and 4.2 microns, and a high altitude layer with exhibiting signals between 4.2 and 8.5 microns. The findings indicate the power of James Webb to be able to probe, for the first time, the vertical profile of the atmosphere of a brown dwarf. And, in fact, there's no reason the Webb telescope has to stop there. As the research paper describing the findings concludes, this is the first such study but will not be the last. In the next few observing cycles, James Webb will transform our understanding of both brown dwarf and young giant exoplanet atmospheres. Number 9. Rings around the Ring Nebula. The Ring Nebula, also known as Messier 57, in Lyra ranks among the sky's most beautiful planetary nebula, the end state of sun-like stars. James Webb has revealed intricate details in the ring itself, which comprises some 20,000 clumps of molecular hydrogen. But what really sets Messier 57 apart in images captured by James Webb is a series of 10 concentric arcs beyond the main ring's outer edge. Astronomers think the arcs first formed near the dying star when ejected gas interacted with a low-mass companion that orbits at a distance about that between the Sun and Pluto. Number 10. Diving into protoplanetary disks. Planets form in dusty, gaseous disks surrounding young stars. Webb's observations not only have provided unprecedented detail in these protoplanetary disks, but also tantalizing clues of precursors to life. Around the nearby star Fomalhaut, the telescope found 3 nested belts of warm dust, suggesting that planets shaped the disk. The observatory also detected water vapor in the inner disk surrounding PDS 70, showing that any terrestrial planets forming there would have access to water. And in the protoplanetary disk surrounding the young star D203506 in the Orion Nebula, James Webb discovered the methyl-cation, a molecule that likely plays a key role in interstellar organic chemistry and the genesis of life. Number 11. A moon of Uranus could have a hidden ocean. Using the James Webb Space Telescope, astronomers discovered that Ariel, a moon of Uranus, could be hiding in a buried liquid water ocean. The discovery could supply an answer to a mystery surrounding this Uranian moon that has perplexed scientists. The fact Ariel's surface is covered with a significant amount of carbon dioxide ice. This is puzzling because at the distance Uranus and its moons exist from the Sun, 20 times further out from the Sun than Earth, carbon dioxide turns to gas and is lost to space. This means some process must refresh the carbon dioxide at the surface of Ariel. Previous theories have suggested this happens as a result of interactions between Ariel's surface and charged particles trapped in Uranus's magnetosphere that provide ionizing radiation, breaking down molecules and leaving carbon dioxide, a process called radiolysis. However, new evidence from James Webb suggests the source of this carbon dioxide could come not from outside Ariel, but from its interior, possibly from a buried subsurface ocean. Because chemical elements and molecules absorb and emit light at characteristic wavelengths, they leave individual fingerprints on spectra. The team behind this discovery used the Webb telescope to gather spectra of light from Ariel, which helped them paint a picture of the chemical makeup of the Uranian moon. Comparing this to simulated spectra from a chemical mix in the lab here on Earth revealed to the team that Ariel has some of the most carbon dioxide-rich deposits in the solar system. Not only did this add an extra 10 millimeters of thickness to the ice on the side of the tidally locked Ariel that permanently faces away from Uranus, but it also revealed clear deposits of carbon monoxide for the first time. As team leader Richard Cartwright from the Johns Hopkins Applied Physics Laboratory said in a statement, "It just shouldn't be there. You've got to get down to 30 kelvins or minus 243 degrees Celsius before carbon monoxide's stable. The carbon monoxide would have to be actively replenished, no question." That's because Ariel's surface temperature is, on average, around 18 degrees Celsius warmer than this key temperature. Cartwright acknowledges that radiolysis could account for some of this replenishment. However, observations from Voyager 2's 1986 flyby of Uranus and its moons and other recent findings have suggested that the interactions behind radiolysis could be limited because Uranus's magnetic field axis and the orbital plane of its moons are offset from each other by about 58 degrees. That means that the majority of the carbon-oxygen compounds seen on Ariel's surface could be created by chemical processes in a liquid water ocean trapped under ice on Ariel. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.